Hi everyone, I'm Ben.
And I'm Kaveh.
All right, today we'd like to take you on this adventure about how you can actually exploit security flaws in hardware, two different kinds of flaws, from software that actually then weaken security properties of software, something that typically is not an assumption that software people make.
So we are part of FUSEC, which is a security research group in Amsterdam. You can see a photo of us there. So here's Ben and me here. There's also Herbert sitting there, and we are hoping to hire Pietro next over there. And so we do defensive and offensive security research. And yeah, we're based in Amsterdam. So if you're around and want to chat, just let us know. And here's our Twitter handle. So if you want to be updated about the stuff that we do, I recommend that you follow us. So today we're going to talk about hardware issues, as Ben mentioned. And here you can see like a classic hierarchy of software on top of hardware. And typically like the upper layer in the stack trusts the lower layer. So if you're an application, you trust that your kernel behaves correctly. And then if you're a kernel running on top of hardware, you would expect that the hardware behaves as you expect it to do. And by hardware, I mean like your CPU and your DRAM and many of the devices that you have, like GPUs and like network cards and things like that. And hardware is solid, right? We all trust hardware. And we think that they don't leak stuff or they don't break. And we oftentimes have this assumption because we believe that hardware is like this house of cards that people have placed together on top of each other very carefully, making sure that it all works as you expect it to work. But I have bad news for you. It's actually in reality looking like this. It's not a simple house of cards. It's actually a stack of, it's like a castle. And all of these like small components, if you just take one of them out, suddenly the whole security of the system is going to break down. And today we're going to show you how we managed to take two of these cards out and how it brings on the entire security of the system. In the first attack that we're going to talk, which we call ANC, we're going to show how the memory management unit of your processor, when it does address translation, is going to leak information. It's going to basically leave a trace in the cache. And we're going to use this to compute virtual addresses of data and code. And since this is secret, this is basically gonna lead to a compromise of data that you're not typically allowed to see, which is your randomized code and data. So you might have heard of ASLR, which is like this security mechanism that we all rely on today. So almost all computing devices rely on these randomized locations so that attackers can't compromise your system when there is a bug. But with this channel, we actually show that we can compromise the system. And the scary part of it is that this can be executed from JavaScript because it relies on such a basic property of the system. And we tried this on many different architectures, like from AMD, Intel, ARM, and we show that all of them actually suffer from this. So the takeaway of this part is that we can basically attack the CPU to leak secrets that we are not supposed to know about. And after this, we're going to talk about another attack the previous one is about leaking, and then the next one is going to be about arbitrary corruptions in memory. And this is possible using hardware, vulnerability that you might have heard of. It's called Rowhammer. And we use Rowhammer, which is basically a glitch in memory that allows you to flip bits to build this attack primitive that we call Flip Feng Shui. And with Flip Feng Shui, we can flip a bit in a memory of a victim with some constraints that I'm going to talk about. And we showed the instantiation of the Flip Feng Shui attack in a cloud setting where malicious VM flips a bit in the memory of a victim VM. And this allows us to compromise OpenSSH, so we can actually SSH into a victim VM or compromise its GPG signatures and make it install packages. So this basically allows us. So the previous one was a read primitive that we built on using hardware, and this one is a write primitive in a sense, like a bit flip that we also exploit using a hardware flaw. So the takeaway is that these attacks, they're all driven from software, and they exploit a flaw in hardware, and we don't actually rely on any software bugs. So these attacks compromise the system or help compromising the systems without any issue in software. They're just exploiting hardware, a low-level hardware issue from a high-level process that is being executed on the system. Okay, so now I'm going to pass over to my colleague Ben, who's going to tell you all about ANC.
All right. Thank you, Kaveh. This is all planned, of course. I want to talk about the this side channel first, which is this mechanism through which, through sneaky kind of side channel observations, we're going to be able to leak some information out of the MMU, out of the CPU, that we're not supposed to be able to know. And I'll talk about why that has security implications first. But even firster, this teaser says what are we going to be able to do at the end of this treatment, which is from JavaScript. This is kind of a visualization thing. At the top is a visualization of memory access latencies. So these are different cache lines, and these are measurement numbers, and these are kind of, well, we're trying to matching up the observations with our kind of hypotheses. Doesn't matter, I'm going to get into that later. So this is a visualization and sort of a report, all from JavaScript, that in the end will result in the fact that we can compute full 64-bit virtual addresses of this data block and a full 64-bit address of this code block. And I find it still a little bit mind-boggling that that's even possible from JavaScript without using any kind of information leak vulnerability. This is all pure side channel observation and computation. So that's what we're going to be able to do. So what is the point of this? Why is this a security problem? Well, that goes all the way back to the 90s. In the 90s, the stack was typically always mapped at the same place. The stack was executable, and the application was mapped at the same place. That means that if you have even a single memory error, like a buffer overflow on the stack, it makes it possible to override the return address on the stack. You can even put code ready to go on the buffer that you're overflowing. Tell the CPU to jump into that buffer, and you can do everything you want. So it's instant, full compromise. And in the 90s, that was relatively easy. And that's possible because the stack has a known address, and it's possible because the application has a known address, and it's possible because the stack is executable. In response to that, there are several mitigations in place nowadays. One of them is ASLR, Address Space Layout Randomization. That means the stack is mapped at an unknown place, the application is mapped at an unknown place, and these are 64-bit random numbers, kind of, not with that entropy, but okay. So it's very high entropy position. So you cannot guess where the stack is. You cannot guess where the application is without a separate vulnerability to get this information out of there, information leak vulnerability. So without that, you cannot exploit easily a memory error like I was describing, because the stack is not executable. You don't know where the stack is, and you don't know where the application is. So what that means is that virtual addresses, right, the location in memory where these things are located, have kind of been upgraded to security-sensitive secrets. So virtual addresses are secret now because if you know them, it becomes easier to exploit. So that's the point of why the side channel that we're going to discuss is a security-sensitive problem. What are side channels? A side channel is something that a way to leak information out of a system through a side effect of how the system works. You've seen this in the movies, right? Instead of trying, if someone wants to break into a safe, you don't try all possible safe combinations. That's impossible according to its design. However, if you're kind of clever and you have a stethoscope and you know how the safe works, as a side effect of how the safe works, you can guess, you can hear, click, clack, click, what the real combination is that the safe is trying to test for, and you can get the combination and break into the safe. Exactly the same way, we're going to listen to activity in the CPU and the side effects that it leaves in the CPU cache, we're going to kind of listen to and recompute virtual addresses that it's translating, even if it's someone else's virtual addresses, thereby breaking this security mitigation. So, number one, the first thing we have to understand to see how this all comes together is how a CPU treats virtual addresses. A CPU needs virtual addresses to do anything. Everything it does using virtual addresses, executing code, loading data, storing data, all that stuff. But everything that it does to the RAM, it does using physical addresses. And they're not the same thing, because then everyone would have to share the same address space that has no end of drawbacks. Therefore, there's a translation so that every process sees its own sparse address space. And there's a mapping from each process's virtual address space to a physical address space. And that mapping happens using a data structure in physical RAM that the operating system sets up called the page table. Page table is actually a tree of page tables, and translating a virtual address to a physical address is a step-by-step operation that ends starts with a virtual address, ends with a physical address, and it is a tree traversal actually, of always 4 steps in the case of 64-bit. So let's take and this is the process that leaves kind of footprints that we're going to observe to find out what the translation was. Okay, so let's look at how a translation works. We want to translate the 64-bit address here. We start at the top level page table, which is always the same for every, per process, always the same. We take the first 9 bits. The first 9 bits translate to 1 of 512 slots in this page table, 1 of 512 page table entries. We go to that slot, that's 8-byte entry, which, among other things, contains the physical address of the next step, and that next step depends on the slot. So let's go to the next step. It's 1 level down. That's 1 step of the traversal. The next 9 bits will similarly tell us a slot in that level, and so on until we reach the last level, and then the last 9 bits of the virtual address give us the slot number that points to the physical address of corresponding to the virtual address that we're looking up. And all this happens on page level granularity, so it's 4K at a time. Now, doing all this stuff really in memory takes an eternity for a CPU. So the memory access are roughly 100 nanoseconds, cache access are roughly 10 nanoseconds, so it would be insane for every single memory access to need this whole process, right? Nothing would ever happen if this were necessary for every instruction. So we cache this information very aggressively. First of all, in the TLB, translation look-aside buffer, it goes straight from a virtual address all the way to a physical address. But failing an entry in the TLB, we also cache this information in the regular old CPU cache, right? All those blocks there are picked from the cache if they're available. And this is what allows us to observe what this MMU is doing, because if we can kind of see where in the page this thing is being cached, this tells us directly something about the virtual address, right? Because these first 9 bits here in the address determine what the offset within this page is. And that's the thing we're going to kind of build up to compute the virtual address with. All right, how do we do that? Second step. DRAM can be huge, but it's relatively slow for a CPU. To make it as fast as possible, we put as much of the DRAM as possible that's being used into the CPU cache. So imagine DRAM might be 8 gigabytes, a cache might be, I don't know, 8 megabytes, roughly that order of magnitude. But unfortunately, the cache is not perfect. So you cannot cache absolutely anything from DRAM absolutely anywhere in the cache. That would be great. But there's a limitation because it has to be fast. The limitation is that the DRAM is partitioned into groups. Each group can only go into its own cache set in the cache. So all this DRAM is competing with a huge amount of other DRAM for its own really tiny little cache set of only 12 or 16 entries. So the cache could be half empty, but you're still doing evictions from the cache because the cache set of the thing that you want to cache is filled up. So that's an inefficiency in this cache architecture that we can exploit to do some cache monitoring tricks. So how does it work exactly? All of this, if this is DRAM and this is cache, then every block from this column, going down as far as big as DRAM is, and every block is 64 bytes, it doesn't really matter. Everything in this column, as soon as it has to go into the cache, can only go into one of these 2 blocks. It can't go here, 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 or here. It has to go into its own column. So all of these things get cached here. All of these things can get cached here. There's no choice. There's this strong partitioning. So let's see how this might work in practice. So we start with the empty cache. Now we're going to access a couple of DRAM cells and see what that does to the cache. So every column, we're going to access cell number 1. It ends up in the cache in the first column. So it's always follow its own column like this. 3 goes into column number 3. Entry number 7 goes into column number 7 in the cache. Memory entry number 18 goes into column number 8. And doesn't depend on the row, right? It only depends on the column where the thing is cached. So let's look at entry number 17. Now, one cache set is already filled up here, see? So if you access any entry from this column here, it has to evict something from here because that's where it has to go. It can't go in any of the free places. It has to go into its own cache set, which is full. So unfortunately, 7 is kicked out, even though the cache was half empty. And that's the property that we're going to use to assemble eviction sets. And eviction sets are a small set of addresses that that all go into the same cache set, and if you access them all, that cache set will be gone of stuff that was there before, because it's now filled with your eviction set. Let's look at an example. Column number 2, we're going to access all that stuff all the time, and with every single access, there's an eviction from the cache. And the important thing is that everything in the same cache set has the same page offset. So this is a memory page, and this is a memory page, and everything in this cache set comes from the same offset within this page. See, all this cache set contains all of the first page cache lines. All of these things in the cache set are all second page cache lines. As in, within a page, it's the second cache line. And that's very important because it means that if we start to access our eviction set and then clearing stuff, we have to remember which cache line that is, because that tells us something about operations that slow down as a result, and I'm going to get to that in the next step. So let's put those two things together. On the left we see a page table walk. On the right we see the effects that this walk has on the cache. So we start again at the page table walk. We want to do translation, right, from a virtual address to a physical address, and that has the usual effect. We access the top level first, and we imagine that it's this slot that we need. That thing, as a result of that page table walk, which the CPU it's not an instruction doing this, right? It's happening as a side effect of an instruction, because it has to access, it has to do this translation from virtual to physical. So as a side effect, the CPU fetches this cache line, it gets cached here, and that's interesting, that as a side effect of this operation, we get this. And it's not a coincidence that we end up in the middle of this cache here, right? Because the page is laid out like this. These are all the first cache lines. These are all the last cache lines. First, last, middle, middle. So next level down, we have to end up like we're sent to this page. We access this cache line. It's the one before last. And that's cached right at the end of this page here, because these cache lines are slightly bigger than page table slots. And the last level, similarly, is cached here. And if we do sequential accesses like this, we fill up the cache also sequentially like that. And if we can find, by looking at the cache activity, where these lookups happen, then we can reconstruct the address, because this says something where this thing is accessed within that page, says something about that address, right? Because we took 9 bits from the virtual address, accessed into this page here, and if we can find out what that is by looking at the cache activity, then we can reconstruct that part of the address, and if we do it with everything, we can reconstruct the full address. So let's see how that might work. So how that might work is, first of all, we always have to evict the TLB, because that short circuits the whole lookup process, and we need the lookup process to monitor it. So we always say we evict the TLB by accessing a bunch of other pages. Then the target that we want to de-randomize, the target that we want to measure the virtual address of, we touch it, and we measure how long it takes to touch it. And then we evict the TLB again, and we touch it again. The second time we know that access is completely cached. All of the page table cache lines will be in the cache, so then we know the cached access time. If we keep doing this, but this time we're going to access one of our eviction sets, so we know that corresponding cache set is empty, and we then measure the lookup time that it took for the page table walk to happen. If it slows down, we know it used the first cache line somewhere. If it slows down, we know, and if it slows down as a result of our first eviction set, we know it uses the first page table slot somewhere. So somewhere in that address are 9 zeros. And we do this for all of the eviction sets that we collected. So if we keep doing this, we're going to find 4 ways it slows down, because there are 4 levels, 4 page tables used. And if we know all of them, we are well on our way to finding out which address there is. So how might this work? We're going to do a page table lookup with this thing. This is the cache that the thing is going to be cached in, but also the cache we're going to be playing with now. And this is DRAM. So let's look at one of those page tables. This page table is going to be stored in DRAM here. So let's put those elements there. So this is physical RAM, and this is the cache. Now let's tell the CPU, look up this address, right? Our target virtual address. What will it do? It'll fetch this cache line, because this is the page table slot that it has to access to do the lookup, to do the page table walk. So it accesses that thing, it goes into the cache. We can see that slow, interesting. Let's do it again. It accesses from the cache. This time it's fast, interesting. Let's try, and because we don't know this from the program, let's try and find out which eviction set I have to touch to slow this operation down. So let's try eviction set number 5 first. We access it both. That cache set is evicted because it's filled with our eviction set. Let's try the lookup again. Come on, CPU, do the lookup for us. It's still cached, it's still fast. So we know, okay, we did not slow the process down. Let's access a different eviction set. Let's access eviction set number 4. This thing gets cached, then 4 gets cached. Now the page table cache line is evicted. So now let's do the lookup again. What happens? Now we go to RAM. And that's 10 times slower than going to the cache. And we can measure this difference. This means, because we know where this eviction set of ours is within a page, it's near the end, we also know that somewhere in that lookup, this cache line was used, this page table slot was used. So now we know 9 bits of the virtual address somewhere. And by trying many variations of our target address, we can make that solution completely unique. Okay, so this we can do from native code quite easily, but, well, compared to JavaScript. But that's not really a big deal, right? Because in native code, you already know all your own addresses. You're only looking at your own secrets. There's absolutely no op in terms of security. But can we show that this can cross a security boundary? Yes, we can. We can make this work from JavaScript even. And that means that we've leaked this information from within this managed language that we're not supposed to know any of the addresses of. We can compute the code addresses and the data addresses of JavaScript objects. And that means if there's a bug in the JavaScript runtime, it's going to be much easier to exploit because you have already the layout of the code and the data available to you as a result of this side channel. Again, without using any software bug. Some complications, unfortunately, not enough time to talk about it right now, but one of the things we had to do to make this work in JavaScript is find a way to do high resolution timing. That's not very easy in JavaScript. In fact, it was specifically made hard to avoid attacks like these, but we found a clever way around it in Kaveh. There are other things that make it trickier in JavaScript, like allocating a huge amount of memory. But the bottom line is we do have working proof of concepts in both Firefox and Chrome. How fast is this? It only takes a few seconds to throw out to get a huge amount of information of the address. Then it takes quite a few more seconds to make that solution unique. So it takes about 40 seconds for this to be a unique, high confidence solution in the virtual address. Where does it work? Everywhere. We didn't try it on JavaScript everywhere, but we did try the native code on all of these microarchitectures, and this is a demonstration of it working on, or a table of it working on Intel, ARM, and AMD CPUs, and in total 22 different microarchitectures on which it all worked. There's no CPU that we found on which this did not, on which the CPU did not have this visible effect. All right, so that is, in a nutshell, how this side channel works. We make the lookup happen, we observe what happens to the cache, and by lots of these observations and piecing it together, we can figure out what the full address is. Now, for the second part of this talk, I would like to give the floor to Kaveh, who's going to talk about something else.
Thanks, Ben. So this was quite crazy, right? By just doing like memory accesses, you could figure out virtual addresses in JavaScript. So this was our leak reading primitive, arbitrary, but not arbitrary, but so like constrained, but still quite powerful read primitive. And now I'm going to tell you about our write primitive. And so the name of the attack that we came up is Flip Feng Shui. Flip means like flipping a bit, and Feng Shui means like organizing your memory object in a way so that this flip actually does quite a bit of damage. And so like our threat model is having a malicious VM in the cloud. So this is something that if an attacker has some credit card, could easily like spawn a VM to a cloud provider of choice. And then the aim is owning the other VMs running on the same machine. This happens quite often. Oftentimes, like you have tens of VMs packed in the same physical machine, and this is how cloud providers make lots of money. And the idea is using like this. So like the flipping part of this comes from so like the Rowhammer bug, which I'm going to briefly mention, and the Feng Shui part of the attack is going to come from memory deduplication, which is this so like process of trying to find out many of the similar pages in the system and only keeping one copy. Because if I go to a cloud, I start like a Linux VM or a Windows VM, and probably this is what you would do as well. And then these VMs are going to share lots of similar pages. So if the cloud provider is smart, can basically find these pages out and just keep one copy instead of making many of the duplicate copies. And this is memory deduplication. And what Flip Feng Shui provides you is like this primitive that allows you to flip a bit in a target VM. And now I want you to think in terms of, if this is Christmas and then Santa is to bring you some present, what would you flip so that you would be able to compromise this VM? We're going to come back to this later. So about Rowhammer. So what is Rowhammer? You might have heard about it in the news. It's a DRAM glitch that allows you to flip a bit somewhere in memory that is not necessarily under your control. And so you would think that this is crazy, right? So your DRAM is something that you think is reliable. You write some data to it, and then when you read it back, it should be the same. That's what you would expect. But this is actually not the case. So people have shown recently that actually 80% of DDR3 DRAMs and some DDR4 modules are also vulnerable to this, that if you manage to read very, very quickly from some locations in that DRAM, some other locations, so some charges start to leak because the transistors have become really, really small, right? And then the error margins have also become quite small. So if you read very, very fast, so the DRAM cannot keep up with refreshing it fast enough because DRAM is basically something that is a dynamic memory, so it needs to be charged every time. It's not stable. And so if you can read quite fast, enough charge will leak that suddenly your 1 becomes 0. And this has huge security implications, right? Because if you can just change a bit from 1 to 0 somewhere in memory that you don't have access to, this has bad implications, right? And typically this doesn't happen because you would expect if this is something that happens regularly, then people would have noticed and they wouldn't have let all these DRAMs to be deployed. But typically what you have is several layers of caches. You have all the CPU caches that Ben just told you about. And your DRAM itself also has some levels of caches. And because of these caches, oftentimes many of these memory accesses are absorbed by these caches. But if you do your accesses in a certain way, then you can actually hit the exact DRAM, the way that would result into charge to leak so that you would see this. So I'm very briefly going to talk about how DRAM is organized. If it is not clear, you can later ask me. So typically, you have a bunch of rows that are stacked together in DRAM, and then you have a bunch of columns. And then if you want to access a certain bit, you have to provide the row address and then the column address. And then from there, you can find the data that you've stored there previously. And typically, the way Rowhammer works is that you choose 2 rows as an attacker, and then you try to read from them very quickly. And reading from these rows, and these rows, by the way, are called aggressor rows. And if you could read from these rows very, very quickly, enough charge will leak from rows that are close by to this aggressor's row to the point that bits start to flip from the processor's point of view. And if you make them close to each other, there will be one row that will be sandwiched, that this is also called the victim row, and then the chance that actually a bit flip would occur will be quite high. So typically that is what the attacker will do. He'll choose some of these rows, and then the attacker will start reading from one of the aggressor rows. And then it will try to read from the other one. And then it will do it many, many, many times. And then at some point, one bit in the middle will flip. And this is the write primitive that we rely on. And how would you do that in the cloud? So you start a VM, and there's typically a hypervisor that makes sure that one VM cannot modify the memory of the other VM. But both of these VM have access to the same hardware. And what we're saying here in this talk is that you can't always trust the hardware, right? So what the attacker VM would do, it would look into its own memory and start reading from it, looking for bit flips, little by little. So the attacker tries but doesn't find bit flips. Tries again, but doesn't find bit flips. But the attacker is very diligent, right? So we try again, and then it would find a bit flip. And here's where your bit flip is. And but so now you have a bit flip, right? But it is your own memory as an attacker. How would you force the victim to store its data into this location? And this is where memory deduplication comes into play. So as I said, so cloud providers try to avoid wasting memory resources because memory is quite expensive. It's quite limited, right? So you want to only store one copy for the data that is duplicated in the system. So here's an example of how it works. So you have a victim VM, like allocating some memory and writing some data. And here's the attacker doing the same thing. And if the attacker knows the content of a page that the victim has, it could basically write it there. And then at some point, the memory deduplication process in the background is going to look for these pages. And it's going to figure out that, oops, there are 2 pages that are the same here. So what it's going to do is that it's going to update the page table of one of these 2 and make it point to the same location in physical memory. And then from that point on, both of these, so like VMs are going to read from the same location in memory. And everything is going to be fine as long as they read. If one of them needs to do a write, there's going to be a copy on write event, and then each of these VMs is going to get its own private copy so that it will be fine. So that's how memory deduplication preserves correct semantics in the system. But now you know that memory cannot be trusted. So what the attacker can do is basically, if it's not the content, it's going to write it in a location where she knows there's going to be a bit flip there. And then once the memory deduplication process is going to come into play, it's going to merge them. And then at that point, the attacker can trigger Rowhammer and corrupt the data that the victim has. Now, back to the question of what would you flip? So anybody has any idea of, you need to know the content, and if you flip a bit, you can compromise the victim VM. So many of you might have heard of this talk. So, for those of you who haven't heard of, do you have any ideas of what you can flip to actually compromise the victim VM? Page table, I heard? Interrupt vector table. Yeah, that would be interesting. But yeah, so that would be one target that you could choose. But then what would happen is that the victim, it would be quite a strong DOS attack, because at some point the victim is going to get an interrupt, for example, and yeah, it's going to crash because the interrupt vector table is going to be corrupted. So we thought quite a bit about this to see what would be a nice target. And we found out with 2 juicy targets. Maybe you can come up with other juicy targets. And the first one was cryptographic public keys. So all of you have used something like SSH, I hope. And then, who has used SSH? Hopefully many of you, yes. This is something that, you're like, we computer scientists, we are lazy. We like to work from home sometimes. So, and that's why we have created things like SSH so that we could work remotely and not go to work. And if you have SSH, and some of you don't like to also type your passwords all the time, right? So then we have created this authentication mechanism based on public key cryptography, where we upload our public key somewhere, and then from that point on, you don't need to even type your passwords. So all is good. And so that's something that you can target. I'm going to show you how this targeting would allow you to compromise the system. And the other thing that we thought of that would be good is domain names. So there are some domain names stored in your target VM that if you flip a bit, suddenly the VM starts fetching data from places where it, for example, wants to fetch some data from Google, but instead of Google, it will go somewhere else. And this is also useful for doing some attack. If you put your public RSA key into, an OpenSSH server in this location, this authorized keys file, from that point on, whenever you want to, log in to this VM, the OpenSSH server is going to read this file, and it's going to bring this file because it wants to know, the public key to actually ensure that you indeed are the one who has the private key by doing a challenge and response. And during this process, it's going to bring this file into memory, into page cache, right? So memory is a big cache for your disk because your disk is slow. Similar to the way that caches are making accesses fast from DRAM, which is slow. And DRAM is not something that you can trust anymore. So, typically, what you have, RSA is that your public key is made out of 2 very large primes that are multiplied together. And the entire, integrity of the scheme is based on the fact that it takes you a very, very long time to factorize this public key into its building primes. And so if you could actually do that, which people have shown would take enormous amount of time, then you can generate the private key, and then from that point on, you could compromise the victim. But if you target if you target the public key, the RSA public key, and you flip a bit into this public key, suddenly this property breaks down. And instead of this public key being a multiplication of two large primes, it becomes a multiplication of many small primes. And then suddenly it becomes very, very easy to factorize it. And once you factorize it, you can generate the private key and you can SSH to your victim VM. And then this is the way that we use to compromise OpenSSH.
Does this really work?
We don't know. We'll see, I guess, if you have time. And then this is nice that it works, but it assumes that we have knowledge of who our target VM is. So we need to know the public key, right? Now you could go to GitHub if I know that, okay, Ben is using the same host, and I know that he also uses GitHub, and I know that his public key is going to be there, so maybe I can try to find out his public key. But wouldn't it be nice if it would be a completely zero-knowledge attack? And then this is also what made us think in terms of what else could we attack. And we came up with this second attack that allows us to compromise apt. And the way it works is that, so typically if you use a Ubuntu or Debian system, or it doesn't matter, Android, Windows, whatever, all of these have a URL where they try to fetch packages from. And if you could flip a bit into this URL, so here, for example, we have Ubuntu. If you could flip a bit there, you could, for example, make it ubuntu.com. And then if the attacker has bought this ubuntu.com domain, suddenly the victim VM is going to go to ubuntu.com, which is nice, right? Well, not for the victim, but for the attacker. The problem with this is that people have been doing this attack for such a long time, right? You have all these network spoofing attacks, R poisoning. So people have been known about this attack for a long time. So what they do is that they try to do integrity checks. So they do end-to-end security by making sure that the packages are signed properly, so that before installing them, they could check their integrity. And this is also something that would stop us from doing this attack. Fortunately, we can do a round 2 of Flip Feng Shui by doing a bit flip into this file that holds the key that is used to verify the signature of these packages. And basically the attack would work as if we flip a bit in the domain, and then we also flip a bit into this file, and then we, again, similar to SSH, we have factorized these GPG keys, and so we could sign our own malicious package, and then the victim is going to come to our repository, download our package, and happily install it like there is no tomorrow. And then after that, you wait a day because, apt-get upgrade runs as a cron job usually, and then the next day, the victim is going to upgrade our package. It could be a compromised OpenSSH or something else. Ben will show you the something else part. So we have, so these are all the exploitable domains that we have figured out. One bit flip away from ubuntu.com and debian.com. There are about 50, 60 of them, and they're up for grab for the highest bidder. No, I'm kidding. We have collaborated with Interpol to make sure that these are blacklisted, so that people could not use Flip Feng Shui to abuse these attacks. Okay, now that I've told you about Flip Feng Shui, I'm going to quickly pass to Ben, who's going to talk about demos.
All right. So is this thing on? Great, thank you. So we've told you a huge amount of stuff in almost no time, but to prove to you that this actually works, we have some videos showing that this stuff works. 2 of them. First, there's a video of of ANC working. So it's this address de-randomization attack. And what I'm going to show you is, apart from some copyrighted music, by the way, sorry Cooper, is a visualization of, hey, let's access all these cache lines, evict every cache line one by one, see if the target address lookup slows down or not. That shows up as a red block. All the blue stuff is remaining possible solutions, and as you'll see, the blue stuff gets smaller and smaller and we're going to solve one page table level at a time. So let's see how that goes. Okay, these are 4 page table levels. We're going to solve them one by one. This is the lowest level. We still have 96 candidates out of 512 remaining after the first few measurement iterations. As soon as all of these things, as soon as remain is 1, 1, 1, 1, then we have a unique solution. So let's see if it works. Thank you, thank you. Shall we also show them Flip Feng Shui or not?
Yeah, why not?
Okay.
They've been a good audience.
Yeah, yeah, indeed. Okay, this is your reward. So let's see. So, Flip Feng Shui, this is the... Do you remember the updates attack that Kaveh was telling you about? The updates attack is... Alright, so I'm going to say something about this. So this is the real Rowhammer attack working, right? It's called Deduplication, real Rowhammer, real VMs, the works. Here we have installed our malicious repository. This is the web server activity for our malicious repository that we're going to send the victim to. This is also the malicious repository where we're going to do some malicious signing. This is the progress report of the attacker, and this is the victim doing totally normal, real victim stuff. So let's see what the victim is going to do. The victim is first going to do a normal apt-get update. Now we're going to do another upgrade. But first, Kaveh,
Does it work?
Do you remember what ls normally looks like?
I don't know. I haven't read the man page.
Okay, let's see how this works. This is what ls normally looks like. But imagine, I don't know what you're going to do, but imagine if he installs a malicious core utils package. ls is backdoored. Thank you, thank you.
Thank you.
It worked this time.
Yeah, surprisingly.
All right. Should we tell them about the ponies? All right, so this work has been quite well received. The Pony Awards, the annual Black Hat Pony Awards, if you're aware, are awards that Black Hat gives out. Both Flip Feng Shui and ANC were nominated for Pony Awards this year. So Flip Feng Shui was nominated for Best Cryptographic Attack. ANC actually won a pony for Most Innovative Research, so that's something that we as a group are very proud of. Also, additional recognition from Apple is that they shipped a mitigation against ANC last year, which was nice of them to mention. Victor went to collect our awards. So yeah, the conclusion as far as we're concerned is that side channels exist that leak secrets. Rowhammer exists to corrupt memory. Hardware is not as flawless and as clean as you might think. It can break and can leak. So take a look at these project pages if you want, and follow us on Twitter.
Thank you.
Thanks for your attention.